The Congo Rainforest is the second largest rainforest on Earth. From above, it looks like a sea of green stretching to every horizon. From inside, it looks like nothing else on this planet. The canopy overhead, a solid, unbroken ceiling of leaves and branches stretching between 30 and 40 meters above the ground, about 100 to 130 feet, intercepts so much of the incoming sunlight that only 1 to 2% of it reaches the ground below. Not dim, not shaded. Darkness in the middle of the day while the sun burns overhead. The air at floor level is absolutely still, warm and dense with the chemistry of thousands of organisms breathing simultaneously. No wind, no sky, just the slow breathing dark. Something large is moving through the undergrowth 30 feet away, not fleeing, not approaching, moving with the unhurried certainty of a creature that has no natural reason to fear anything in this forest. It has been doing this, in this forest, in this darkness, for longer than the concept of a city has existed anywhere on Earth. This forest does not measure time the way the rest of the world does. It has its own clock, its own weather, its own rules, and it has been running by them without interruption for millions of years. When the last ice age came and glaciers scraped entire continents bare, when the great forests of Europe collapsed, when the Sahara dried, when the megafauna of North America vanished one by one, this forest held. It did not shrink into fragments. It did not recover afterward. It simply continued the way it always had, while the world around it was remade from scratch. 500 million acres, larger than Alaska, of a world that refused to end. And because it survived, it kept things the rest of the world lost. Animals that disappeared from every other place on Earth are still here. Ecosystems that existed before human civilization are still intact inside this forest, running the same way they ran before the first city was ever built. In 1901, Western science formally discovered a horse-sized relative of the giraffe living inside this forest. In 2007, scientists described a new monkey species from a living animal that local communities had already known for generations. Then, in 2017, researchers discovered something even older beneath the trees, the world's largest tropical peatland, an underground archive roughly the size of England, storing an amount of carbon equivalent to around 3 years of global fossil fuel emissions. Until then, science had not fully understood what was beneath the forest floor, and the forest itself remained largely unmeasured. The first atmospheric research tower in the Congo Basin only began operating in October 2020. An ancient ecosystem had been regulating its own atmosphere while much of the scientific world was still looking in from the outside. 1 in 5 living species on Earth can be found here, and beneath the trees, an entire prehistoric world is still operating. This forest is still revealing itself, still holding things back, still running a version of the world that everywhere else has already ended. Tonight, we're going into the Congo to uncover what survived here, what still remains hidden beneath the forest floor, and why this ancient ecosystem may be doing far more to keep the modern world functioning than most people realize. Before we go further, a quick like and subscribe helps support the channel and gives us the chance to keep bringing more stories like this. And if you're kind enough to share, I would love to know, are you listening to this to sleep, or are you wide awake and genuinely curious about what lives in this darkness? Let me know in the comments. Now let's step into the darkness beneath the canopy. The Congo did not survive the ice ages by remaining unchanged. Its forest moved with the climate, retreating into places where moisture endured, then spreading outward again when wetter conditions returned. Across millions of years, that rhythm turned geography into protection. During the Pleistocene epoch, which lasted from 2.6 million years ago to 11,700 years ago, repeated glacial cycles transformed the world's landscapes. In Africa, cooler and drier periods pushed rainforest boundaries backward as grasslands expanded. Forests became separated into refugia, small regions where suitable conditions persisted. In the Congo Basin, some of these refugia endured around coastal Gabon, the lower Congo, and protected river valleys. Elsewhere, the contractions were more destructive. Parts of the Amazon lost enormous areas of continuous forest. Southeast Asian rainforests repeatedly shrank as climates changed. Across northern regions of the world, advancing ice eliminated forests over enormous distances. The Congo experienced pressure too, yet its geography offered several forms of protection at once. The basin sits astride the equator, where sunlight remains strong throughout the year, and rainfall can continue even when conditions become difficult elsewhere. Mountains and elevated land surrounding parts of the basin create a broad bowl, helping moisture remain within the region. Water arriving as rain does not immediately escape. It gathers through an immense network of rivers, wetlands, and lowlands, feeding the forest from within. The Congo River became especially important during the Pleistocene. Its modern course developed roughly 1.5 to 2 million years ago, creating a powerful internal drainage system across the basin. As surrounding landscapes became drier, this network continued carrying water through the heart of the forest. The basin therefore possessed its own source of resilience, with rainfall entering a landscape already shaped to retain and redistribute it. The Sahara also played a role through its distance. North African drying events could push vegetation boundaries dramatically southward, but the Congo's interior lay far enough from that influence to preserve substantial areas of forest. The result was never complete isolation from climate change. Forest margins contracted, species ranges shifted, and open landscapes expanded between surviving patches. Those surviving patches became refugia in the fullest sense of the word. Plants and animals that could persist there remained connected to a living forest, while populations elsewhere disappeared. When wetter conditions returned, these populations expanded outward. Some met relatives from other refugia. Others remained separated long enough for their differences to accumulate through generations. That cycle repeated across immense stretches of time. Forest contracted, endured, expanded, and contracted again. Each repetition left behind another layer of evolutionary history. Species adapted to particular valleys, wetlands, soils, and rainfall patterns. Populations became isolated, then reunited, carrying differences shaped by the places that had sheltered them. The Congo's great advantage was therefore not a single wall against the past. It was a collection of geographic conditions working together, giving life places to retreat without disappearing completely. The forest could bend without breaking, preserving populations until the climate allowed them to spread again. Over roughly 1.6 million years, those refugia became more than shelters. They became chambers where evolution could continue while the wider world changed around them. The Congo endured because, when the planet became hostile, it still contained places where life could wait. And inside those places, evolution never stopped. A river can become a boundary without anyone drawing a line. In the lower Congo, water itself creates that boundary, occupying a channel so deep and forceful that the landscape seems to change scale around it. At its deepest measured point, the riverbed lies about 219 meters below the surface, which is about 720 feet. That depth would swallow a 60-story skyscraper beneath the waterline. The river also spreads more than 24 kilometers across in some places, which is about 15 miles, making the opposite bank difficult or impossible to see from the water. Its banks can feel less like shores than edges of another continent. The Congo carries roughly 1.4 to 1.5 million cubic feet of water each second, a discharge exceeded among the world's rivers only by the Amazon. All that water moves through a channel that becomes increasingly constrained toward the Atlantic. The resulting force creates rapids and cataracts on a scale rarely encountered in any river system. Near the river's mouth, the Livingstone Falls stretch for about 354 kilometers, which is about 220 miles. Across this reach, 32 cataracts interrupt the river, turning the surface into a succession of steep drops, whirlpools, and turbulent channels. Henry Morton Stanley, who encountered this stretch during his expedition, compared its violence to a storm driven sea. His description captured something important about the river's character. Its power is not occasional, it is built into the geography. For animals living along its banks, such a river becomes more than water to cross, it becomes separation. Large terrestrial mammals do not regularly move across the lower Congo, and the combination of depth, current, breadth, rapids, and crocodile habitat creates a formidable biological boundary. Once populations become divided for long enough, even members of the same ancestral species can begin following different evolutionary paths. The Congo reached its modern configuration roughly 1.5 to 2 million years ago during the Pleistocene. Around this period, the populations ancestral to today's bonobos and common chimpanzees became separated on opposite sides of the river. The exact history is more complicated than a single moment of division, yet the geography provides a compelling setting for their divergence. Biologists call this process allopatric speciation. A population becomes divided by a physical barrier, gene flow between the groups is reduced or stops, and generations begin accumulating differences independently. Given enough time, those differences can become so substantial that the separated populations form distinct species. The Congo therefore became part of an evolutionary experiment written into geography. North of the river, chimpanzees followed one social and ecological path. South of it, bonobos followed another. Their common ancestry reaches back to a population that once occupied a shared landscape, while the river transformed that shared space into two worlds. The remarkable part is that the boundary remains physical today. Water still occupies the channel. The same geography continues to separate the forests on either side, preserving a division that began deep in the Pleistocene. Evolution left its mark in the river itself, turning a current of water into a wall between two living branches of one remarkable lineage. A bonobo moves through the forest with a body built for life among branches, vines, and fruiting trees. Its face is dark, its limbs are long, and its movements carry a familiar intelligence that makes the boundary between human and ape feel unusually thin. Yet this animal belongs to a world that exists in only one corner of the planet. Wild bonobos live exclusively in the Democratic Republic of the Congo, in lowland forests south of the Congo River. Their range is naturally restricted by the rivers surrounding their habitat, leaving them with one of the smallest geographic distributions of any great ape. Every wild bonobo alive today belongs to this forest system. There is nowhere else where a naturally occurring population survives. Their closest living relatives are chimpanzees and humans. Bonobos and chimpanzees share a common ancestor, and their lineages separated roughly 1 to 2 million years ago. Humans share about 98.7% of their genetic material with bonobos, a similarity that places these apes remarkably close to us in evolutionary terms. Their resemblance reaches beyond anatomy. Both species form intricate relationships, learn from one another, communicate through varied calls and gestures, and remember individuals across long periods. On the northern side of the Congo River, chimpanzee societies developed with a different social balance. Males generally hold higher rank. Alliances among males can determine access to territory and resources, and neighboring groups may engage in lethal territorial conflict. Infanticide also occurs, particularly when males take control of a group and eliminate infants fathered by rivals. These behaviors form part of a social system in which competition and coalition building are deeply woven together. Across the river, bonobo communities display another arrangement. Females tend to outrank males, and female alliances can help maintain that position even though males are physically larger. Mothers remain closely connected with their offspring, while females form strong bonds with one another. Food sharing, grooming, play, and physical contact help maintain relationships across the group, and conflicts are often reduced through social interactions rather than prolonged physical aggression. This does not make bonobos incapable of aggression. Males can be aggressive, disputes occur, and individuals compete for food, mates, and social standing. The difference lies in how those pressures are organized within the community. Female cooperation can limit male dominance, while strong social bonds give individuals several ways to repair relationships after tension. Their society also has an unusual fluidity. Bonobos often divide into smaller parties while searching for food, then reunite with larger groups later. Individuals can move between these temporary gatherings, maintaining connections across a wider community. Such a fission and fusion pattern allows social relationships to remain flexible while preserving a shared group identity. The river may have separated the ancestral population, yet geography alone did not determine the final character of either species. Forest resources, competition, maternal relationships, and countless generations of social learning shaped what happened afterward. The same ancestral inheritance produced two living primate societies with strikingly different balances of cooperation, hierarchy, and aggression. For the bonobo, that evolutionary history remains tied to one place. Its world is the forest south of the Congo River, where generations have followed paths through trees that their ancestors also knew. A species found nowhere else continues its existence there, carrying one particular branch of primate history forward through every generation. The first recorded scientific encounter with an okapi began with a trail of reports that seemed difficult to reconcile. Local people in the forests for generations already knew the animal, while European naturalists remained unaware that such a creature lived among the trees. By 1901, evidence had reached Western science, and the animal entered zoological history as one of the most extraordinary large mammals to be documented in the modern era. An adult okapi has a deep brown coat, with sharply defined black and white bands covering the upper legs and rear of the body. Its long, flexible tongue can reach places that seem awkward for an animal of its shape, including its own ears. The combination gives it an unusual appearance, almost as though several familiar animals had been assembled into one forest specialist. Its resemblance to a zebra, however, comes from stripes that evolved independently under the particular lighting conditions created by dense vegetation. Those markings may break up the outline of the body among shafts of light, trunks, and leaves. In a forest where illumination arrives in fragments, a pattern of alternating dark and pale bands can make an animal harder to distinguish as a single moving form. The okapi's appearance therefore reflects its surroundings with remarkable precision, shaped through generations in a habitat where visibility works differently from open grassland. Its deeper story reaches far beyond its coat. The okapi is the only living relative of the giraffe. Their shared lineage extends millions of years into the past, when giraffe relatives occupied a much broader range across Africa and Eurasia. The giraffe eventually became specialized for feeding high above the ground, developing an elongated neck and legs suited to open environments. The okapi followed another path, retaining a body better suited to moving through dense forest and feeding among vegetation close to the ground. That separation makes the okapi more than an unusual mammal. It represents a surviving branch of giraffe evolution that avoided the environmental pressures that shaped its better known relative. Its anatomy carries traces of that history, while its daily life remains tied to the forest that sustained it. Okapis feed on hundreds of different plant species, selecting leaves, shoots, ferns, fruits, and other vegetation from the forest understory. They generally live alone, with individuals maintaining ranges that overlap without forming large, permanent herds. Females give birth to a single calf, and the young animal spends its early life concealed among dense vegetation while its mother forages nearby. The species is restricted to the northeastern forests of the Democratic Republic of the Congo, particularly around the Ituri region. Its dependence on this habitat is profound. Remove the forest, and the okapi loses the food, cover, pathways, and ecological conditions that have shaped its existence. When the okapi became known to Western science in 1901, the discovery changed the meaning of the forest itself. A large mammal had been living there without appearing in the scientific record, carrying an evolutionary history that reached deep into the past. The forest had been mapped in broad strokes, yet one of its most distinctive inhabitants remained entirely outside those maps. Its discovery showed that the Congo could still hold an entire chapter of natural history that the modern world had never read. In June 2007, a monkey entered the scientific record from the Middle Lomami Basin in Central Democratic Republic of the Congo. The animal had already been part of local knowledge for generations. People living in the region knew its appearance, its behavior, and the places where it moved through the forest. It even had a name, Lesula. What changed in 2007 was not the animal itself, but the moment science finally documented it. The Lesula is a medium-sized primate with a distinctive face, long limbs, and a reddish-brown back that fades into paler coloring around the chest and underside. Its range is remarkably restricted, occupying lowland rainforests between the Middle Lomami and Upper Chwapa rivers. Surveys found that populations were concentrated within this region, making the species an endemic of Central Democratic Republic of the Congo. Its status as a separate species was established through two different kinds of evidence. Researchers compared physical characteristics, including body form and facial features, while genetic analysis revealed differences separating the Lesula from its closest known relatives. The discovery therefore rested on more than appearance. Anatomy and molecular evidence converged on the same conclusion: a distinct primate lineage living in a forest that had already supported it for generations. The story carries an important detail about how knowledge moves through a landscape. Scientific recognition arrived after local recognition. Communities had observed the animal directly, understood where it lived, and incorporated it into their knowledge of the surrounding forest. The formal description gave the animal a place in scientific literature, yet its existence had never depended on being written down. That distinction matters in the Congo because the forest remains difficult to survey at the scale required for complete biological inventories. Dense vegetation limits visibility, rivers divide habitats, and many species occupy specialized environments that can be reached only through long field expeditions. Some animals are active for brief periods, others live high in trees, and many insects, fungi, amphibians, and plants can pass through an entire human expedition without being encountered. Even repeated surveys may reveal only a small portion of the living community present there at any moment. The Lesilla was a primate, large enough to see and socially complex enough to attract attention. Even so, it remained outside the formal scientific record until the early years of the 21st century. That places the discovery in a different category from finding an extinct creature in fossilized rock. The animal was alive, reproducing, moving through its habitat, and sharing the forest with people, while the wider scientific world remained unaware of its status. Researchers continue to expect additional discoveries across the Congo Basin, especially among insects, amphibians, plants, fungi, and other organisms that receive far less attention than large mammals. Thousands of species are thought to remain undescribed, although the exact number cannot be known until more of the basin is surveyed. The Lesula therefore represents something larger than one new entry in a species list. It shows that the scientific map of the Congo is still incomplete in the present tense. A living primate could remain outside that map until 2007, while local knowledge had carried its identity across generations. In this forest, discovery is still an ongoing process, unfolding one organism at a time. At the base of the Congo forest, sunlight becomes a scarce resource. Only about 1 to 2% of the light arriving above the canopy reaches the ground, leaving the floor in persistent dimness even around midday. A canopy rising roughly 30 meters, which is about 100 feet, intercepts most of the radiation before it can touch the leaves below. That limited light shapes the floor itself. Large plants compete poorly beneath such conditions. So much of the ground is occupied by fallen leaves, mosses, seedlings, and small ferns. Every layer of decomposing material becomes part of a biological cycle. Leaves fall, fungi break them down, insects feed among them, and nutrients return to roots. The surface is therefore less a collection of debris than an active processing system, continually converting dead material into resources for living organisms. The canopy also buffers conditions close to the soil. Daily changes in heat and moisture are softened before they reach the ground, creating a comparatively stable environment. Fungi can process wood and leaves without exposure to direct sunlight. Insects complete portions of their lives among the litter, while amphibians and other small animals use moisture held around roots and decaying vegetation. Human senses are poorly adapted to this setting. With so little light available, distance and scale become difficult to judge, especially when an animal crosses the leaf litter without warning. A spider only several inches across can appear much larger when its body is briefly outlined against a dark floor, giving an ordinary encounter an exaggerated presence. The Congo supports several large tarantulas, including members of the Hysterocrates genus. These heavy-bodied spiders spend much of their lives associated with burrows, where they wait for insects and other small prey to pass nearby. Their underground retreats connect the surface world with cavities beneath roots and fallen material, turning a small patch of ground into a hunting territory. Other African tarantulas occupy the trees instead. Stromatopelma calceatum is an arboreal species associated with hollows, bark, and elevated vegetation. Its long legs and climbing ability suit a habitat where the ground is far below, while its medically significant venom makes encounters unsuitable for inexperienced handlers. The forest floor and vegetation above therefore support very different forms of spider life. Among Baka communities of Central Africa, there is also a traditional account of a giant spider called Jaba Fofi. Descriptions portray a brown, tarantula like creature with a leg span of roughly 1.2 to 1.8 meters, which is about 4 to 6 feet. It is said to build webs across paths and shelter beneath roots. These accounts have been passed through generations, yet no specimen has been formally collected and no confirmed photograph has established the animal as a distinct species. Several explanations remain possible. Large known spiders may appear exaggerated in poor light. Multiple webs can sometimes create the impression of one enormous structure. Local observations can also refer to animals that science has not yet documented. The Congo has repeatedly shown that scientific absence is not proof of biological absence, although every claim still requires physical evidence. The forest floor holds that uncertainty naturally. Its biological processes continue whether anyone records them or not, and much of its activity occurs outside ordinary human observation. A giant spider may belong to folklore, misidentification, or an undiscovered species. At present, the evidence cannot decide between those possibilities. More than 40 meters above the ground, which is about 130 feet, the Congo changes character. The forest that seemed enclosed from below opens into moving air and intense sunlight. Broad-leaved crowns spread across the upper reaches, forming a living landscape where branches, leaves, insects, birds, and climbing mammals occupy different levels. Trees in the basin can reach roughly 40 to 49 meters, which is about 130 to 160 feet. At these heights, conditions differ sharply from those around the roots. Sunlight arrives directly, wind moves freely between crowns, and temperatures can change more rapidly. Animals adapted to the understory may rarely encounter species living above them, even though both occupy the same forest. There is also space between the trees. Branches frequently remain separated instead of forming one continuous surface, creating gaps that canopy animals must cross. Some climb around the openings, while others leap, glide, or fly between neighboring crowns. For a squirrel, monkey, bird, or insect, the distance between two branches becomes part of the landscape itself, a stretch of open air woven into daily movement. Above the main canopy stand emergent trees, their crowns rising into direct sunlight. These uppermost trees create small islands of habitat, exposed to stronger light and moving air. Birds use their branches as feeding and nesting sites. Insects gather around flowers and leaves, and epiphytes settle onto bark and limbs. These plants grow on other plants while remaining separate from the soil, collecting moisture and nutrients from rain, dust, and organic material gathered around their roots. The canopy also shelters animals found nowhere near the ground. Primates travel along branches, birds search among leaves, and insects spend entire lifetimes in the crowns. For these species, the upper forest is a complete habitat, with feeding, shelter, courtship, and movement, all taking place above the soil. The canopy also participates in the movement of water. Millions of trees release water vapor through transpiration, sending moisture upward from leaves into the atmosphere. As that moisture cools and condenses, clouds develop and rain returns to the forest. Water can therefore pass repeatedly between vegetation, air, rivers, and soil, helping sustain rainfall across the basin. The trees participate in a circulation system that reaches far beyond any individual crown. Research indicates that trees there tend to be taller and more widely spaced than those in comparable forests of Southeast Asia and the Amazon. Elephants and other large animals consume, damage, or remove smaller trees and vegetation, reducing competition around the larger trunks. Resources can then be concentrated among fewer, taller trees. Every additional meter of height, which is about 3.3 feet, brings a tree closer to stronger sunlight. The competition begins at the crown and continues downward through layers of leaves. Most incoming light is captured before it reaches the ground, leaving only a small fraction for plants below. The darkness at the forest floor is connected directly to the architecture overhead. From the highest emergent crown to the roots below, the Congo forms one connected system of light, water, air, and life. The canopy is a habitat, a passageway, and a mechanism for moving moisture through the forest. Its height gives the basin another dimension, turning the forest into a series of living worlds stacked above one another. The shape of the Congo forest can be changed by footsteps, tusks, and appetite. The forest elephant moves through vegetation as a force of disturbance, opening paths, breaking stems, and altering which plants gain access to space and light. Its influence reaches far beyond the animal itself because the forest has evolved around its presence. The African forest elephant is a distinct species from the savanna elephant. Its body is smaller and darker, while its tusks generally point downward, a useful form in dense woodland where large upward curves would catch more easily among branches. These features belong to a life spent moving through vegetation rather than open grassland, where every journey is shaped by trunks, vines, roots, and fallen wood. One of the most important effects appears among young trees. Forests of Central Africa tend to contain taller trees and fewer small trees than comparable forests in the Amazon and Borneo. Large herbivores help create this pattern by feeding on young growth, trampling vegetation, and opening patches where new plants must compete for space. Elephants are especially influential, repeatedly disturbing the lower layers and preventing dense thickets from becoming permanent. Their clearings, known as base, become gathering places within the forest. Mineral-rich soil draws elephants and other large mammals to these openings, where animals consume mineral deposits and vegetation unavailable elsewhere. The repeated use of these places keeps them open, creating a changing mosaic inside the surrounding woodland. Paths leading toward them can become established routes, remembered and reused across generations. The elephant also carries the forest from one place to another. Fruits swallowed during feeding may contain seeds that later pass through the animal and are deposited far from the parent tree. This movement gives plants opportunities to establish beyond the immediate reach of their original crowns. Some tree species depend heavily on large animals for this service, linking the survival of individual plants to the movements of creatures that can travel for 10 kilometers, which is about 6.2 miles, through the forest. A single journey can therefore connect distant parts of the woodland, carrying genetic potential into places where a new tree might otherwise never take root. The scale of this relationship becomes clearer when carbon is considered. A 2012 study estimated that old-growth forests in Central Africa stored about 39 billion tons of carbon in vegetation and tree trunks. The tall trees, holding much of that carbon, exist within a community shaped by herbivores that continually influence which smaller plants survive. Remove large numbers of elephants, and the pattern changes. Small trees can become more numerous, crowding the lower forest and altering competition for light, water, and nutrients. The shift may seem gradual when viewed from a single clearing, Yet across thousands of acres, it can reshape the structure of the woodland itself. Elephants therefore occupy a role deeper than that of a large herbivore passing through trees. Their feeding, movement, trampling, seed dispersal, and use of mineral clearings form part of the forest's operating system. Their roots carry inherited knowledge, their diets redistribute plants, and their disturbances create room for different generations of trees. The Congo is shaped by organisms that continually modify one another's world, and the forest elephant is one of the strongest forces within that living design. Somewhere among the trees of Central Africa lives a bird whose closest living relatives are separated from it by an entire continent. The Congo peafowl is the only true peafowl species found outside Asia, an animal whose existence seems to belong to a different map. Its feathers, behavior, and lineage carry a history that makes the geography around it feel strangely incomplete. Peafowl are native to Asia. Their nearest relatives, their known evolutionary history, and their surviving distribution are centered there. The Congo peafowl occupies a completely different landscape, restricted to lowland rainforests of the Democratic Republic of the Congo. It does not appear as a recent visitor or an introduced population. It is a distinct African lineage within the pheasant family, established in a forest separated from Asia by thousands of miles. Its scientific discovery was almost accidental. In 1936, the American zoologist James Chapin recognized an unfamiliar feather among specimens in a museum collection. The feather had been labeled as belonging to another bird, yet its structure suggested something far more unusual. Chapin eventually traced the mystery to the Congo, where living birds confirmed that the strange feather belonged to a species science had never formally recorded. The discovery carries a particular kind of strangeness because the bird was already part of the forest. Local communities knew it. The animal had existed there through generations of human observation, while scientific collections still lacked a name for it. Its delayed appearance in the scientific record shows how difficult the Congo can be to survey, especially when species occupy dense forest and populations are scattered across remote habitat. Biogeography gives the bird an even older story. The presence of a peafowl lineage in Africa raises questions about how its ancestors reached the continent and how their descendants became isolated from their Asian relatives. The Congo peafowl does not provide a complete answer, because millions of years have erased many of the routes and landscapes through which earlier populations may have moved. Ancient climate shifts, changing forests, and movements of land and animals can leave behind distributions that look puzzling when viewed only from the present. The species survives within a restricted region of central Congo rainforest, where its population is difficult to survey, and its habitat continues to face pressure. Its rarity makes every surviving population significant. There is no second continent holding another wild population, no distant reserve containing a separate natural branch of the same species. Its entire living story remains tied to this particular forest, where generations have survived within a narrow ecological refuge. The Democratic Republic of the Congo has made the Congo peafowl its national bird, giving this unusual species a place in the country's identity. That choice carries a fitting symbolism. The bird represents something the forest repeatedly demonstrates, that the past can remain alive in forms whose origins are difficult to reconstruct. A single feather once waited in a museum drawer before revealing an animal that should have been impossible to overlook. Yet the forest had been carrying its lineage all along. The Congo peafowl is more than an isolated African bird. It is a surviving fragment of a much older biological geography preserved in a place where the boundaries of the present still fail to contain the stories of the past. The forest floor has another layer of history, one that remained beyond ordinary sight. Beneath leaves, roots, and the dark soil is a body of peat so extensive that its discovery changed the way scientists understood the Congo Basin. In 2017, researchers revealed that this region contains the largest tropical peatlands known on Earth, stretching across a landscape whose importance reaches far beyond the trees growing above it. Peat is compressed, partially decomposed organic matter. Plants fall into waterlogged ground where oxygen is scarce, slowing the processes that would normally return their remains to the atmosphere. Layer after layer accumulates, preserving material that might otherwise disappear. In the Congo, some peat deposits reach depths of 7 meters, which is about 23 feet. Their formation began more than 10,000 years ago, allowing carbon captured by plants long ago to remain stored underground across thousands of seasons. That makes the peatlands more than a reservoir of carbon. They are a physical record of changing conditions, written vertically through the earth. A lower layer can contain traces of vegetation that lived thousands of years earlier. Another layer above it may preserve evidence of a different climate, a different pattern of rainfall, or a shift in the surrounding forest. The ground itself becomes a sequence of environmental moments, compressed together until the past can be read from material that once belonged to living plants. The scale is difficult to grasp. The peatlands extend across an area comparable to England, forming one of the largest continuous tropical peat systems on the planet. They store an extraordinary quantity of carbon, estimated to equal several years of global fossil fuel emissions. Much of that carbon has remained underground because saturated peatlands keep dead vegetation from decomposing completely. Their discovery also carries a human story. Scientists did not arrive with instruments and independently uncover a landscape that had been invisible to everyone. Local Congolese communities had known these deep swamp forests for generations. Their knowledge identified places where the ground remained saturated and unstable, guiding researchers toward landscapes that had received little scientific attention. The formal discovery entered scientific literature in 2017, while the knowledge of the people living around these wetlands was far older. The peatlands, therefore, reveal something important about how little a forest can surrender to distant observation. Satellites can trace vegetation, aircraft can cross the canopy, maps can divide rivers and borders into precise lines. None of those tools, by themselves, revealed the full depth of what was stored below the ground. For thousands of years, plants had been falling into these wetlands, becoming layers of preserved organic matter instead of returning their carbon to the atmosphere. The process continued through generations of people, through changing climates, and through the rise and disappearance of societies elsewhere. The Congo carried this buried record without announcing it. What makes the peatlands extraordinary is their combination of scale, age, and concealment. They are a landscape beneath a landscape, a living forest above a geological archive below, preserving evidence of environmental change that can still be examined today. The discovery in 2017 did more than add another feature to the map. It revealed that even in the modern age, an entire geography could remain beneath our feet, waiting for someone to understand what the forest had been holding. The Congo is doing something difficult to see from the ground. Every leaf, root, trunk, and pocket of soil belongs to a system that moves carbon through the living world and back into the atmosphere. Across the basin, this exchange has become part of the planet's climate machinery. Trees draw carbon dioxide from the air during photosynthesis, storing some of that carbon in wood, roots, and soil while returning oxygen to the atmosphere. The scale becomes clearer when the forest is viewed as a whole. The Congo Basin removes roughly 600 million metric tons of carbon dioxide from the atmosphere each year, more than it releases through human activity and natural processes combined. That amount represents a substantial share of global emissions, giving the basin a role far larger than its position on a map might suggest. Its trees are functioning as a living reservoir, continually taking atmospheric carbon and placing part of it into biological material. Some comparisons have found the basin's net carbon uptake to be several times stronger than that of the Amazon when measured against forest area and other conditions. Among the world's great tropical forests, the Congo remains especially important because large areas of intact forest still stand. The Amazon and Southeast Asian forests have experienced extensive clearing and degradation, reducing their ability to remove carbon at their former strength. The Congo retains a greater portion of its original forest cover, allowing its carbon cycle to continue at a planetary scale. What looks like wilderness from a distance is therefore participating in an exchange that reaches far beyond Central Africa. Rainfall is part of the same machinery. Water drawn from the soil moves through roots and trunks before leaving leaves as water vapor. That moisture enters the atmosphere above the forest, where it can condense into clouds and return as rain. The cycle helps sustain the vegetation that drives it, creating a relationship between forest cover, atmospheric moisture, and rainfall. When enough forest remains intact, the system can reinforce itself across enormous distances. Climate scientists describe the Congo, alongside the Amazon, as a potential tipping point system. Large changes in rainfall or forest condition could weaken the processes that keep moisture moving through the basin. As trees disappear, less water returns to the atmosphere through transpiration. Drier conditions can then make further forest loss easier, creating feedback that can spread through connected parts of the ecosystem. The concern reaches beyond individual trees because the climate system depends on these connections operating together. Direct measurements of this machinery arrived surprisingly late. The first atmospheric flux tower in the Congo Basin began operating in October 2020. For much of modern climate science, researchers were studying a major planetary carbon system without continuous measurements taken directly from inside it. The forest had been exchanging gases, moving water, and storing carbon throughout that entire period, whether anyone was recording each movement or not. Seen this way, the Congo is more than a surviving fragment of an older world. It is active infrastructure built from living organisms and water, soil, sunlight, and atmosphere. Its importance comes from processes happening every day, across roots and leaves, clouds and rivers, trunks and peat. The forest does not announce its work. It simply continues the exchange that keeps its own world functioning, while also helping shape the conditions beyond its borders. At night, the Congo does not become empty of sound, it becomes layered. The first impression may come from insects and frogs near the ground, a shifting texture of clicks, pulses, trills, and calls. Higher in the vegetation, branches carry movements from animals that rarely descend. Far above, leaves respond to changes in air, while trunks and limbs flex under their own weight. The forest has no single voice. It is an acoustic community occupying different heights, distances, and frequencies at once. Some of its largest voices exist outside the range of ordinary human hearing. Forest elephants produce very low frequency calls that can travel for long distances, allowing individuals to communicate when trees and distance separate them. Elephants can detect sounds at frequencies far below human hearing, and research indicates that low frequency signals can travel more than 10 kilometers, which is about 6.2 miles, under suitable conditions. Elephants also respond to seismic vibrations transmitted through the ground. Their feet can detect vibrations, giving the animals another channel for information that human ears cannot follow. Then there is the gorilla chest beat. An adult male stands upright and strikes his chest rapidly with cupped hands, creating a deep drumming display that is both visible and acoustic. Recordings of mountain gorillas show that this sound can be heard from more than 1 kilometer away, which is about 0.62 miles. The deeper frequencies also carry information about body size, with larger males producing lower peak frequencies. In dense vegetation, where sight is often limited, a sound can cross the forest before the animal itself comes into view. Closer to the water, another kind of presence belongs to the pygmy hippopotamus. This small forest relative spends much of its life around streams, swamps, and thick vegetation, usually alone. Its vocal repertoire includes grunts, squeals, and other calls used during encounters and interactions. The animal moves through habitats where sound travels around trunks, reeds, pools, and tangled roots, adding another thread to the nocturnal acoustic fabric. Modern recording equipment has begun to reveal how much information exists in these layers. Researchers working in Central Africa have deployed networks of acoustic recorders that operate around the clock, collecting enormous libraries of bird calls, primate sounds, insects, frogs, and mammal activity. One public recording project in the northern Congo alone contains more than 1 million hours of continuous sound. And the recordings also expose the limits of what is known. A microphone can remain in one place for months, collecting signals from species that a researcher may never encounter visually. Night after night, the same forest produces a changing arrangement of frequencies, shaped by rainfall, temperature, breeding cycles, movement, and social behavior. Each layer carries information shaped by another living process nearby. Standing there, human hearing captures only part of the transmission. Some sounds arrive as obvious calls. Others reach the body as vibration or exist below the threshold of the ear altogether. The Congo's night is therefore more than a collection of noises. It is a biological network carrying information through air, wood, water, and soil, a communication system operating across distances and frequencies that humans evolved without needing to hear. Three great apes move through the Congo Basin along different paths shaped by food, landscape, memory, and social life. Gorillas, chimpanzees, and bonobos all belong to the same broader primate family, yet their worlds have developed distinct rhythms. Few places allow researchers to consider these lineages within one enormous forest system where related animals have been responding to changing ecological pressures across millions of years. Their presence turns geography into part of the evolutionary story because every river, ridge, clearing, and food source can influence which behaviors remain useful and which relationships endure. The gorilla lineage separated from the lineage leading toward chimpanzees and humans roughly 10 million years ago. Much later, chimpanzees and bonobos diverged from one another, with the Congo River becoming an important geographic barrier between their populations. The river did more than divide land. It helped separate gene flow between groups, allowing differences in behavior, appearance, and ecology to accumulate through generations. Gorillas live largely on leaves, shoots, stems, fruit, and other plant foods. Their societies are often centered on stable family groups, with a dominant adult male providing protection and maintaining cohesion. His presence gives the group a recognizable social structure, one built around proximity, relationships, and long periods of association. In the forest, their strength is expressed through movement and feeding as much as through displays. Chimpanzees occupy a different social landscape. They eat both plant and animal foods, travel through larger communities, and divide into smaller parties that change composition throughout the day. They use tools, remember individual relationships, cooperate with allies, defend territories, and pass learned behaviors between generations. Young chimpanzees acquire many skills by watching older members of their communities, creating traditions that can differ from one population to another. Bonobos follow another route. Their societies are strongly shaped by female relationships, cooperation, and frequent social contact. Food can be shared, tensions may be reduced through affiliative behavior, and conflicts are often managed through social interaction rather than prolonged physical escalation. Their communities show how cooperation can become a powerful organizing force in a large primate society. The differences become especially interesting because these animals are close enough evolutionarily for their contrasts to be meaningful. Each species carries inherited traits from shared ancestry, then expresses them through a different combination of diet, habitat, competition, cooperation, and social learning. The forest becomes a setting in which similar biological equipment can produce very different forms of life. The Congo also contains several major gorilla populations, including western lowland gorillas and eastern lowland gorillas, while mountain gorillas occupy highland forests farther east. Chimpanzees range widely through Central Africa, while bonobos remain restricted to forests south of the Congo River. Their distributions reflect geography written into living bodies, with rivers, elevations, food supplies, and forest boundaries shaping where each lineage can persist. Seen together, the three apes offer something rare in nature. They provide living examples of how intelligence, memory, cooperation, competition, and family life can develop along separate paths while remaining connected to the same deep evolutionary history. Their forests overlap within one continental region. Their ancestors were related, and their lives continue to unfold under the same tropical sky, each species carrying a different answer to the possibilities of being a great ape. None represents a final destination, only one branch among several possibilities shaped by time. The gorilla carries a history measured in millions of years, yet its daily life is made of remarkably ordinary acts. A hand reaches for a stem, leaves disappear between heavy jaws. A family shifts through vegetation, following paths shaped by food and familiarity. Somewhere in that routine is an evolutionary lineage that separated from the lineage leading toward humans roughly 10 million years ago, beginning a distinct history that continues today. That history unfolded across Central African forests through major changes in climate and landscape. Gorillas persisted through the Pleistocene and environmental shifts, adapting their movements and diets while remaining tied to forest habitats. Their survival is therefore written less in dramatic transformation than in continuity. The body remained suited to vegetation, slopes, streams, and dense cover, while generations passed through the same broad setting. An adult male silverback can weigh more than 180 kilograms, which is about 400 pounds, and stand nearly 1.8 meters, which is about 6 feet, tall. He is the largest living primate, a body built around powerful arms and a digestive system suited to a plant-rich diet. Yet size alone does not define his role. A silverback protects the group, settles disputes, guides movement, and remains closely associated with the females and young that form his family. For mountain gorillas in the eastern Congo, the forest rises into cloud covered highlands. Their habitat can reach elevations between 2,400 meters, that is nearly 8,000 feet, and 4,000 meters, which is about 13,000 feet, where cool temperatures, heavy moisture, and steep terrain create conditions very different from the lowland basin. Their lives are adapted to this highland environment, with vegetation providing food and cover through a climate that limits many other large mammals. Far below those elevations, lowland gorillas occupy the broad interior of the Congo Basin. Swamps, tangled vegetation, and difficult terrain make direct surveys exceptionally demanding. Researchers can estimate populations through nests, signs, camera observations, and carefully designed field surveys, yet uncertainty remains. The forest itself becomes part of the challenge. A living animal can remain close while vegetation prevents a clear view, turning population science into a patient exercise in inference. At dusk, a silverback begins preparing a place to sleep. He bends vegetation into a nest, arranging branches and leaves into a platform that supports his body through the night. The structure is temporary, used for a single night before another nest is made. Across generations, this repeated behavior has linked one evening to another, each nest appearing for a few hours before returning to the forest floor. There is something distinctive about this continuity. Human civilizations have risen and disappeared within a fraction of the time represented by the gorilla lineage. Languages have changed, borders have moved, and landscapes elsewhere have been transformed by roads, farms, cities, and industry. The gorilla remains tied to a living environment that still provides the foods, shelter, social relationships, and physical space its lineage requires. The Congo's gorillas, therefore, embody a form of persistence that cannot be reduced to age alone. Their story is carried through bodies, family groups, feeding routes, sleeping nests, and inherited behavior. 10 million years after their lineage took its separate path, a silverback can still fold leaves into a bed beneath the trees, while young gorillas learn the forest by following those who learned it before them. In the Congo, the leopard moves through a predator community with an unusual absence at its center. There are no lions sharing the same forest interior, no cheetahs crossing open ground, and no large packs of African wild dogs competing for the same prey. Spotted hyenas are also absent from this deep forest. The leopard occupies a different kind of landscape here, one where dense vegetation changes how hunting, movement, and competition unfold. Across open savannas, a leopard lives among several powerful predators. Lions can take kills or drive leopards away from feeding sites. Wild dogs pursue prey in coordinated groups, while cheetahs dominate through speed in open country. Such competition places limits on where a leopard can hunt, when it can move, and how it can use its body. Night activity becomes especially useful when direct encounters with larger competitors carry greater costs. The forest alters that equation. Trees, vines, swamps, and narrow passages break the landscape into small hunting spaces, while the absence of several major competitors leaves the leopard with more freedom to exploit them. Congo leopards are reported to reach larger sizes than many savanna populations, a difference associated with habitat, prey availability, and reduced competition. Their bodies reflect generations shaped by conditions that differ from those on the grasslands. A leopard here can move through a forest where the predator guild remains comparatively simple. That does not mean hunting becomes easy. Visibility is limited. Prey can disappear into vegetation within moments, and every pursuit demands careful positioning. The leopard's strength lies in flexibility. It can climb, swim, stalk, wait, and carry prey into trees, adjusting its behavior to a landscape where straight lines are rare. This relationship reaches beyond the leopard itself. A large predator influences which herbivores survive, where they feed, and how heavily they browse particular plants. Those changes can affect young trees, shrubs, and the composition of vegetation. In a forest ecosystem, the path from predator to plant may pass through several species, yet the connection remains real. Predation becomes part of the architecture of the living forest. For most of the world, these relationships have been heavily altered. Large predators disappeared from many landscapes, prey communities changed, and human activity reshaped habitats and movement routes. The late Pleistocene extinctions removed numerous large animals from continents, altering food webs that had developed over long spans of evolutionary time. The Congo retained more of its large mammal community, allowing interactions between predators and prey to persist on a scale increasingly rare elsewhere. The leopard, therefore, offers more than an image of a powerful cat moving through vegetation. It provides a glimpse of predator ecology under conditions where several major competitors never became part of the same forest system. Its presence helps preserve relationships between hunter, prey, vegetation, and habitat that have been fragmented across much of the planet. Each track through damp soil, each abandoned feeding site, and each movement along a forest edge belongs to that larger system. The leopard does not stand outside the Congo's ecology as a separate ruler. Its hunting shapes the lives of other animals. Those animals influence the plants, and the plants alter the places where the leopard can hunt again. The cycle continues through generations, leaving behind a functioning predator network that still resembles an older ecological arrangement. There is a part of the Congo where the names of its animals begin to feel like a catalog of another age. In the northeastern basin, the Ituri forest stretches across a landscape of dense woodland, rivers, swamps, and clearings, forming one of Central Africa's richest centers of life. It is especially known for the okapi, forest elephants, great apes, and the Congo peafowl, species whose survival is tied to this particular forest region. The forest is also home to communities whose knowledge of its paths, plants, and animals reaches across generations. Rain is one of the forces that gives the Ituri its character. Moisture moves through the forest repeatedly, feeding streams, saturating soils, and supporting layers of vegetation from the ground upward. In places where forests have been repeatedly broken apart by drying, cultivation, or other disturbance, species communities can become separated. The Ituri has retained large areas of continuous forest, allowing animals that need deep cover to move through a landscape still connected enough to sustain them. From above, that continuity has always been difficult to understand. A forest canopy can conceal an entire world beneath it, turning the surface into a green pattern while the living structure below remains difficult to observe. During the 20th century, maps and aerial photographs could reveal rivers, clearings, and the broad outline of the trees, yet many details of life on the forest floor remained inaccessible. The density of vegetation was itself a barrier, leaving researchers dependent on journeys through the forest and on observations made from within it. For forest elephants, the Ituri contains places where the ordinary forest gives way to mineral-rich clearings. These natural openings, often called bays, attract animals seeking salts and other minerals that are difficult to obtain from ordinary vegetation. Elephants can return to such places repeatedly, following routes through dense habitat that become familiar within family groups. Their movements connect distant parts of the forest, carrying seeds and altering vegetation as they pass. The same landscape shelters okapi, an animal found nowhere else in the world. Its existence depends on the forests of the northeastern Congo, where it moves through dense vegetation and follows established paths. The Ituri also supports chimpanzees and other primates whose lives unfold across a mosaic of trees, streams, fruiting plants, and forest openings. Each species occupies its own portion of this layered environment, yet their lives remain linked through food, movement, predation, and the physical structure of the forest. The Ituri is not untouched. Logging, hunting, mining, armed conflict, and other pressures have reached into the region, and the Okapi Wildlife Reserve itself has faced serious threats. Its importance comes from the amount of ecological continuity that remains and from the extraordinary concentration of species that depend upon it. The forest survives as a living network, sustained by relationships too numerous to see at once. Here, the prehistoric quality of the Congo is found in continuity rather than isolation. An elephant trail, an okapi path, a fruiting tree, and a primate call belong to the same connected system. The Ituri does not preserve a world frozen in time. It preserves processes that have continued through immense changes beyond its borders, allowing an old ecological rhythm to remain part of the present. For thousands of years, people have moved through the Congo forest as part of its living fabric. Among them are the Aka, Baka, Babangel, Bakola, and Bakoya, communities whose histories are deeply connected to the forest and its seasonal rhythms. Their lives have been shaped by fruiting trees, animal movements, rivers, rainfall, and the changing abundance of plants. The forest is not merely a place they enter to find food. It is a landscape whose signs, pathways, and resources have been learned across generations. Archaeological evidence places human presence in the Congo Basin hundreds of thousands of years into the past. Some sites preserve evidence dating to at least 620,000 years ago, reaching far beyond the history of cities and agriculture. These traces belong to a period when human populations were already moving through Central Africa, long before the emergence of modern societies. The forest, therefore, carries a human history that is extraordinarily deep, woven into the same landscape where other lineages have persisted. For forest hunter-gatherer communities, survival depends on knowing details that cannot be reduced to a map. A particular tree may reveal its season through the first change in its leaves. A trail may indicate where animals have passed. A familiar patch of vegetation can signal food, medicine, or water. Such knowledge is practical, accumulated through observation, memory, and repeated movement across the same territory. Among the Baaka of the northeastern Congo, this relationship with the forest has been especially important. Knowledge of paths, plants, animals, and seasonal conditions can be shared between generations through daily activity, stories, songs, and teaching. A child learning the forest is learning a system of relationships where one observation leads naturally to another. The knowledge becomes useful because it has been tested against the landscape itself. That relationship also became important to modern science when researchers began mapping the Congo's peatlands. Local Congolese knowledge helped guide scientists toward swampy areas containing deep peat, contributing to the recognition of a globally important carbon store. The discovery was therefore not the product of instruments alone. It depended on people who already understood parts of the terrain that outsiders had barely documented. Their way of life has never meant that the forest remained completely unchanged. People hunt, gather, travel, make shelters, use fire, and alter small areas around temporary camps. What matters is the scale and pattern of those changes. Traditional forest use can operate within ecological limits that allow vegetation and animal populations to recover, while industrial extraction and large scale land conversion can transform entire landscapes. That distinction gives the human story another depth. The Congo does not contain a wilderness without people. It contains a wilderness where people have developed knowledge for living within a complex ecological system. The forest elephant carries roots in memory. The okapi follows paths through vegetation. People carry knowledge of those same places in another form, through words, experience, and generations of teaching. That knowledge is vulnerable. Languages disappear. Younger generations move away. Traditional territories are fragmented, and forests are cleared or degraded. When a forest path is lost, more than a route disappears. A piece of accumulated understanding can vanish with it, leaving behind fewer connections between people and the living world that taught them. For much of modern climate science, the Congo existed more clearly on maps than in measurements. Satellites could trace its canopy, field teams could document individual species, and models could estimate its influence. Yet, the instruments needed to observe the forest as a functioning climate system arrived remarkably late. That delay matters because forests are not static objects. They exchange water, carbon dioxide, heat, and energy with the atmosphere every day. One date captures the scale of the gap. In October 2020, the first atmospheric flux tower in the Congo Basin became operational at the Yangambi Research Station. Such a tower measures exchanges between the forest and atmosphere, allowing scientists to track how much carbon dioxide enters and leaves the ecosystem. Before that installation, the Congo had no comparable direct measurement from this kind of instrument, despite its importance to global carbon budgets. The forest had been influencing the atmosphere for generations while scientists were largely watching from a distance. Another date came in 2017, when researchers formally mapped the Cuvette Centrale peatlands. The survey revealed an area of roughly 145,500 square kilometers, which is about 56,200 square miles, larger than England. These peatlands contain an estimated 30 billion tons of carbon and store an amount equivalent to roughly 3 years of global fossil fuel emissions. Their discovery followed years of fieldwork, including expeditions through remote swamp forests, showing how little direct information existed about some of the Congo's most consequential landscapes. The same pattern appears in biology. In 2012, scientists published the formal description of the Lesilla, a monkey previously unknown to the international scientific community. Local people already knew the animal, while researchers were still establishing that it represented a distinct species. The episode became a reminder that a forest can be familiar to the people who live within it, while remaining poorly documented in scientific literature. The imbalance becomes clearer beside Amazonian research. The Amazon has benefited from large, coordinated research programs, long-running measurements, extensive field infrastructure, and decades of accumulated observations. The Congo has received a much smaller share of international forestry research funding. Between 2008 and 2017, the Congo Basin received about 11% of international forestry funding, compared with 55% for Southeast Asia and 34% for the Amazon. The difference is not merely financial. It determines which forests become richly measured systems and which remain dependent on scattered observations. In February 2023, scientists from across the Congo Basin gathered in Libreville and agreed to form the Congo Basin Science Initiative. Its proposed science and capacity plan calls for major investment in coordinated research and training, drawing inspiration from the large programs that transformed understanding of Amazonia. The initiative estimates that about $200 million would be needed over a decade to build comparable scientific capacity. So the missing knowledge is not an abstract absence. It has dates, instruments, maps, species, funding figures, and entire research programs attached to it. Global climate models and biodiversity assessments have been built while one of Earth's great forest systems remained far less measured than its importance would suggest. The Congo has been functioning all this time. Our understanding of it has been trying to catch up. Under the surface of the Congo, evolution has another landscape, shaped by currents, stone, depth, and isolation. Nearly 700 fish species have been recorded across the basin, and many are found nowhere else. The number itself is striking, yet the geography behind it matters more. A river that looks continuous from above is divided underwater into separate worlds, each with its own pressure, speed, temperature, and shelter. Near the river's lower reaches, the Livingstone Falls extend for about 220 miles, creating a chain of cataracts and rapids that separates fish communities from one another. Water surges through narrow channels, drops through gorges, and forms powerful currents that can become barriers as effective as mountains on land. Populations trapped on different sides of these barriers can follow their own evolutionary paths. Closely related fish may gradually acquire different bodies, behaviors, and ecological roles while remaining remarkably close in geography. The river becomes a natural laboratory where isolation can be observed through living species. Then the river drops into depths rarely associated with fresh water. Some sections descend more than 200 meters, which is about 656 feet, and measurements have found even deeper reaches, approaching 220 meters, which is about 722 feet. There, sunlight disappears completely. Pressure rises with every meter, and the animals occupying those depths live under conditions radically different from the water above. One fish made that hidden depth known. The blind cichlid, known scientifically as Lamprologus lethops, was repeatedly found pale, eyeless, and already dead or dying near the surface. Its body carried clues from a place where no living specimen had yet been observed. Gas bubbles beneath the skin pointed toward catastrophic decompression, meaning the fish had risen rapidly from deep water and suffered the physical consequences as pressure fell. What appeared to be an unusual fish mortality became evidence of a river descending hundreds of feet into darkness. The animal had surfaced, carrying a message from a habitat scientists had barely imagined. Other fish reveal the opposite expression of this isolation through size and force. The Goliath tigerfish is among the Congo system's great predators, reaching around 1.5 meters, which is about 5 feet, with a powerful body and large interlocking teeth. Its form belongs to a river where turbulence, prey diversity, and separation between habitats have shaped predators along paths unlike those found in more uniform waterways. The geography itself adds another layer. The Congo is the only major river known to cross the equator twice, carrying its waters through both sides of the equatorial belt. Seasonal patterns, flood pulses, tributaries, rapids, deep channels, and isolated pools create a mosaic of freshwater habitats within one connected basin. Fish populations encounter different pressures depending on where they live, and those differences can accumulate through generations. Down there, The forest has another history. The river carries its own evolutionary record, written in scales, bones, currents, and adaptations that formed without human direction. Some species have been studied for decades. Others remain known from only a handful of specimens, while large stretches of water have received little biological sampling. The Congo's underwater world is therefore more than a mirror of the forest above. It is a separate living archive, still producing discoveries from its darkness. There is a scale to the Congo that becomes difficult to grasp when attention rests on a single animal, a single river, or one stretch of forest. Pull back far enough, and the basin begins to resemble a living catalog written across land and water. Scientists estimate that roughly 1 in 5 of Earth's living species occurs within the Congo Basin, a concentration that places this region among the most biologically important places on the planet. The figures gather quickly. Depending on how researchers define the basin and classify species, the Congo is home to roughly 400 to 450 mammal species, more than 1,000 bird species, hundreds of reptiles and amphibians, and nearly 700 fish species. Those numbers include creatures occupying completely different worlds, from river channels and flooded forests to grasslands, swamp margins, and the high canopy. Each population carries its own history, and many exist nowhere beyond this region. Plants expand the picture further. More than 10,000 plant species are known from the Congo Basin, with around 30% considered endemic, meaning they occur nowhere else on Earth. That places thousands of unique plant lineages within a single geographic system. The smaller numbers are just as revealing. Around 142 reptile species have been recorded in parts of the basin, with 15 found nowhere else. Amphibians number around 139 in the same regional accounting, including 28 endemic species. More than 1,100 butterfly species have been documented, while mammal inventories, in particular areas, record around 270 species, including 39 endemic forms. These figures do not describe a finished collection. They are measurements taken from a living system whose remote sections remain difficult to survey. Geography helps explain why so much diversity can persist together. The Congo Basin is not one uniform habitat. Rivers divide populations. Wetlands create seasonal refuges. Savannas interrupt stretches of woodland, and flooded forests change with the movement of water. At the center of this mosaic lie the world's largest tropical peatlands, storing immense quantities of carbon within waterlogged soils. Freshwater communities develop alongside terrestrial ones, while species move between habitats according to seasons, food, and reproduction. All of this life occupies a landscape covering roughly 500 million acres, with forests that have persisted through major climatic changes across roughly 1.6 million years. A pollinator depends on a flower. A fruiting tree feeds a primate. A predator shapes the behavior of its prey. Fish distribute nutrients through waterways, while insects, fungi, birds, and mammals carry energy through countless connections. The result is a biological record written in living organisms rather than fossils, with new generations continuing processes that began long before human history, while their habitats remain linked across the basin. 1 in 5 is therefore more than a statistic. It describes a concentration of living history held within one interconnected basin, from canopy to riverbed. Every species represents a thread, and every thread belongs to a larger fabric that cannot be understood by counting its parts alone. The Congo's importance rests in that entire web, still functioning across forests, rivers, wetlands, and savannas. Under the forest floor lies a record of climate written in dark, Waterlogged soil. The central Congo Basin peatlands began accumulating roughly 10,000 years ago as plant material collected faster than the wet ground could allow it to fully decompose. Layer followed layer, preserving carbon that had been drawn from the atmosphere by generations of plants long before any human city existed. Today, these peatlands hold roughly 29 billion metric tons of carbon, making them one of the largest terrestrial carbon stores known on Earth. Peat depends on water. When the ground remains saturated, decomposition is slowed, and much of the carbon stays locked away. Drain the soil, expose it to air, and the balance changes. A dried peatland can become vulnerable to fire, and peat does not behave like a fallen branch in a campfire. Flames may appear at the surface, while combustion continues within the soil itself. Smoldering can persist underground for long periods, consuming material that accumulated over thousands of years and returning its carbon to the atmosphere. The danger becomes clearer when the scale is translated into time. During drought, the water table can fall, allowing oxygen deeper into the peat and accelerating decomposition. Earlier drying episodes have left evidence that these changes can already alter carbon storage without any industrial activity. The vulnerability is therefore part of the ecosystem itself. The carbon stored across the Congo's peatlands has been estimated at an amount equivalent to roughly 3 years of total global fossil fuel emissions. That comparison turns a distant reservoir into something easier to understand. A deposit formed over millennia contains enough carbon to influence the atmosphere on a planetary scale if large portions were released rapidly. The peat was formally mapped and its extraordinary extent recognized in 2017, when researchers showed that the central Congo Basin contained the largest known tropical peatland complex. The discovery revealed how much carbon had been accumulating outside the view of most global climate assessments. Later field studies refined the estimate and showed that only a small fraction of the peat carbon lies within nationally protected areas, leaving much of the reservoir exposed to changes in land use. Then came a different kind of pressure. In 2022, the Democratic Republic of Congo announced a licensing round involving 27 oil blocks and 3 gas blocks. Some proposed areas overlapped sensitive rainforest and peatland landscapes, raising concerns that roads, drainage, drilling, and associated development could disturb the water conditions protecting the stored carbon. The licensing round was later canceled in 2024, although the broader debate over resource development in the basin continues. The peat therefore belongs to the present as much as the past. Its carbon is ancient, yet its stability depends on conditions that can change within a human lifetime. The forest canopy helps regulate moisture. Wet soils restrict decomposition. Rivers and rainfall sustain the saturated ground. Together, these processes keep a massive store of atmospheric carbon in a form that has remained contained since the early Holocene. What rests under the Congo is not a fossil sealed away from modern life. It is an active part of the climate system, held in place by water, soil, vegetation, and the continued integrity of the forest above it. For more than 1 million years, the Congo Basin endured changes that arrived on scales no human calendar can easily hold. Ice ages advanced and retreated. Rainfall shifted. Sea levels rose and fell far beyond the basin's interior. Volcanic eruptions darkened skies across continents, while extinctions altered communities elsewhere. Through those cycles, forests contracted, expanded, and found new balances. The system endured because change came through geological time, allowing species, soils, rivers, and vegetation to adjust together. The pressure arriving now moves differently. Between 2015 and 2019, the rate of tree cover loss in the Democratic Republic of Congo approximately doubled. In 2021, forest loss increased again by roughly 5%. Across the previous 2 decades, an estimated 17.1 million hectares of forest were lost. Each clearing may begin as a small opening, yet roads, settlements, farms, and repeated burning can gradually connect those openings into a changing landscape. Hunting adds another layer to the transformation. The commercial trade in wild meat removes animals that evolved as structural parts of the forest community. Forest elephants spread seeds across long distances and shape vegetation through their feeding and movement. Great apes disperse seeds and influence which plants establish beneath the canopy. When these large animals disappear from a region, the effects can travel outward through relationships that are difficult to see from a single clearing. Industrial logging can deepen that change. A road built for timber extraction creates access where little existed before. Trucks carry logs outward, while the same route can later carry hunters, traders, farmers, and settlers inward. What begins as a narrow corridor may become a permanent line through the forest, changing movement patterns for animals and altering the practical boundaries of human activity. The ecological footprint, therefore, extends far beyond the trees removed for timber. Population growth places another weight on the same system. The population across countries surrounding the Congo Basin is projected to grow substantially during the coming decades, increasing demand for farmland, charcoal, timber, transportation, and food. None of these needs exists outside the realities of human life. The difficulty comes from their accumulation inside an ecosystem whose value depends on keeping many relationships connected. The Congo remains one of the world's great terrestrial carbon stores, and large areas still retain the capacity to absorb more carbon dioxide than they release. That distinction matters because forests can lose this function gradually as degradation spreads, even while substantial tree cover remains. A forest may still appear continuous from above while roads, hunting pressure, selective logging, and declining animal populations have already changed how it functions. The contrast is therefore written in two different clocks. Geological change gave the Congo immense spans of time in which life could respond, migrate, adapt, and reorganize. Modern pressures can alter the same relationships within a few decades. A forest that survived continental climate shifts and ecological upheavals can still be transformed by roads, chainsaws, fires, and expanding demand. The Congo is not being tested by one event. It is being reshaped through thousands of individual decisions, repeated until their effects become part of the landscape. The remarkable endurance of the forest makes that transformation more significant because what is disappearing is a system that took far longer to assemble than any human generation will ever have to rebuild. A species can disappear from the Congo without leaving behind anything that can restore it. There may be bones someday, preserved in sediment or uncovered by chance, but the living lineage itself ends at the last surviving individual. With it goes a body of learned behavior, relationships between species, and adaptations shaped through generations. Another animal may occupy some of the same space, yet it cannot reproduce the particular evolutionary history that produced the vanished form. Grauer's gorilla, also called the eastern lowland gorilla, shows how much can be lost while a species still remains. This is the largest gorilla subspecies on Earth, found only in the Eastern Democratic Republic of Congo. Since the 1990s, its population has fallen by more than 77%. Every decline carries consequences beyond the number of animals remaining. Families disappear, feeding traditions are interrupted, and local knowledge of forest resources can vanish with groups that once carried it through generations. The okapi faces a different kind of uncertainty, classified as endangered. It survives in the forests of the Democratic Republic of Congo, yet its current population cannot be measured with confidence and is believed to be decreasing. Hunting for meat and skin becomes especially damaging when protection weakens, because the forest can conceal the scale of losses for years. An animal may become scarce across a region before researchers have enough observations to understand how far its decline has progressed. The Congo peafowl carries another form of uncertainty. Its populations are localized, dispersed through difficult terrain, and challenging to survey accurately. Scientists cannot place a precise total on the species across its range. That absence of a reliable number creates a strange boundary around knowledge. A population can become smaller without producing a clear signal that tells the outside world exactly when it has crossed from rarity into danger. Forest elephants reveal what happens when a species disappears from the places where its ecological influence once reached. Their movement through vegetation can open paths, disperse seeds, and create conditions that favor different plants. Heavy losses from the ivory trade have reduced elephant numbers across parts of the Congo Basin. Where their presence has thinned, the forest can begin to develop differently, with changes in tree communities appearing as one of the long echoes of their decline. The loss is therefore measured in more than bodies. It removes possibilities, including behaviors and ecological partnerships that may never have been observed, understood, or recorded by science. These animals are more than separate entries in a conservation list. Each represents an evolutionary lineage shaped by a particular landscape, climate, food web, and history of survival. Their traits were assembled through countless generations, with every generation carrying a little of the accumulated experiment forward. Once the lineage ends, those relationships cannot be restarted. Captive breeding cannot recreate lost instincts. Genetic material cannot restore extinct behavior or the ecological circumstances that produced it. The Congo still holds living lineages that began their histories millions of years ago. Their continued existence means those evolutionary stories are still being written by reproduction, movement, feeding, competition, and inheritance. Extinction closes that process permanently. There is no later generation waiting to return, no natural mechanism that can reopen the same branch of history. When one of these lineages ends, the forest loses something that existed nowhere else, and the world becomes permanently less complete. For generations beyond the reach of research stations, the forest has been studied by people who never needed to call it a field site. Among Baaka and Baka communities of the Congo interior, knowledge of plants, animals, seasons, soils, and pathways has been gathered through continuous residence across hundreds of generations. Each observation belongs to a much longer record than any expedition can create, because the same places have been encountered again and again as conditions change. A plant is recognized in relation to the season in which it appears, the ground where it grows, the animals that feed from it, and the signs that distinguish one useful species from another. Such knowledge can include changes across elevation and seasonal cycles, patterns that become visible only after years of repeated observation. A research team may enter the forest for a limited period, collect measurements, and leave. Communities living there remain through the entire cycle, carrying observations from one season into the next and comparing them with what previous generations learned. Animals provide another layer of information. A change in bird calls, the movement of a herd, the arrival of particular insects, or the altered behavior of a primate can signal shifts in weather, fruiting, water, or disturbance. These connections are difficult to capture with instruments because they unfold across time and place. A person who knows the forest intimately can recognize a pattern through many small signs that, taken separately, might seem insignificant. The discovery of the Congo's immense peatlands revealed the value of this knowledge in a particularly clear way. Congolese partners already knew about peat-rich areas and understood that they could hold something important. The scientific resources needed to investigate them at scale were largely elsewhere. When researchers eventually mapped the peatlands, the discovery became a scientific landmark, yet local knowledge had already provided part of the path toward finding them. That pattern matters because knowledge can exist long before the means to publish it. The forest has been observed by people whose understanding was built through necessity, memory, practice, and repeated testing. Calling this only oral tradition can make it sound like a collection of stories detached from evidence. In reality, much of this knowledge is empirical. A plant identification can determine whether food or medicine is safe. Reading animal behavior can influence where people travel or where they avoid danger. Mistakes carry consequences that make careful observation part of everyday survival. This creates a record with a scale that conventional science struggles to reproduce. Thousands of individual observations, accumulated across generations, form a living data set connected to particular places. It includes details about species that researchers may encounter only occasionally, seasonal changes that short surveys can miss, and relationships between organisms that become visible only through familiarity. When communities are displaced, when younger people leave for cities, or when access to traditional forest territories is restricted, the loss extends beyond culture. The chain that carries observations from one generation to another can break. A piece of ecological knowledge may disappear without ever being written down, measured by an instrument, or entered into a scientific archive. The Congo, therefore, holds two records of its own history. One is written in species, soils, rivers, and peat. The other lives in human memory, refined through generations of direct experience. Losing either record leaves the understanding of the forest incomplete. There is a moment inside the Congo when the scale of time becomes difficult to keep in the mind. The forest floor sits under a canopy that can filter much of the sunlight, leaving the ground dim even around midday. Trunks rise through layers of vegetation, roots cross the soil, and water gathers in places where peat continues forming from plant material that decomposes only slowly. The surroundings are alive with processes that began long before human settlements appeared. At ground level, the air carries more than warmth and moisture. It contains the products of countless organisms working at once. Leaves break down through fungi and microbes. Roots exchange compounds with the soil. Insects move through fallen vegetation. Water passes through organic matter and carries dissolved material onward. Every breath enters a chemical system shaped by millions of living interactions, many of them occurring beyond direct sight. Look upward, and another timescale appears. High in the canopy, chimpanzees construct sleeping nests from branches and leaves. A nest can sit around 40 meters, which is about 131 feet above the ground. The behavior is learned within chimpanzee communities, then passed through generations, while the impulse to build a secure sleeping place is rooted in a lineage far older than any human city. Each evening, another nest becomes part of the forest's changing architecture. Closer to the ground, Movement follows its own logic. A large animal can pass through vegetation only a short distance away, perhaps 20 feet, that is nearly 6 meters. It does not need roads, property lines, written maps, or borders to understand the space around it. Its world is defined through scent, sound, feeding grounds, shelter, water, and paths shaped by repeated movement. The modern systems that organize human life exist beyond this immediate ecology, while the animal responds to conditions that have governed forest life for generations. That difference in experience gives the Congo its unusual sense of deep time. A human visitor arrives carrying knowledge of cities, satellites, national boundaries, engineered landscapes, and machines capable of measuring distant planets. The forest receives that visitor without changing its rhythm for the sake of human chronology. Trees continue exchanging gases. Fungi continue breaking down wood. Rivers continue carrying sediment. Animals continue following seasonal signals written into food, rainfall, temperature, and daylight. The perspective becomes even more striking when measured against the age of the ecosystem itself. Evidence indicates that the Congo Basin has supported forests through enormous climatic changes, while its present rainforest system has persisted in recognizable form for roughly 1.6 million years. Human beings, by comparison, occupy only a small interval within that history. Cities, written governments, national borders, and industrial economies belong to an extremely recent layer. Standing there, a person becomes the newest arrival in an environment whose relationships predate every institution they know. The sensation has a scientific foundation. It comes from entering a living system whose biological memory stretches across immense spans of time, expressed through species, behavior, soil, water, and cycles of renewal. The Congo does not need to resemble the distant past to preserve deep time. Its present is already carrying it, through living relationships that remain active from one season to the next, with no museum glass separating the observer from the history being observed. The Congo has endured forces that arrived without intention. Cooling spread across continents, rainfall shifted, volcanic eruptions darkened skies, and sea levels rose and fell. Through those changes, the forest had only one problem to solve: remain suited to whatever conditions the planet presented. Survival was a matter of adaptation, migration, contraction, expansion, and renewal. A different kind of pressure now reaches its boundaries. It comes with plans, prices, permits, maps, contracts, and calculations. A logging concession begins as lines on paper before becoming a road through living forest. An oil block can exist first as a boundary on an auction document, marking a place where geology has been assigned an economic value. Decisions made far from the trees can eventually alter the conditions beneath them. That distinction is easy to miss when the threats are described only as another chapter in environmental change. A drought does not choose which valley should lose its trees. A volcanic winter does not identify a particular species as commercially useful. Ice does not study a forest boundary before advancing. Human decisions can do all of these things indirectly because they begin with knowledge of what the forest contains and what those resources might be worth. The Congo has survived immense disturbances because natural forces move through ecosystems without a plan to extract anything from them. Even severe change leaves room for movement, refuge, recolonization, and evolutionary response. A forest can retreat toward wetter regions, species can follow shifting habitats, and isolated populations can persist where conditions remain suitable. Extraction introduces a different sequence. A road removes trees first, then creates access, then brings further traffic, hunting, settlement, and conversion. One decision can alter the conditions surrounding many others. The scale of each individual intervention may appear modest beside an ice age. A concession occupies a portion of a basin. A cleared corridor crosses one landscape. A drilling site marks one location. Yet their effects can spread through connected systems. Forest fragmentation changes animal movement. New access increases hunting pressure. Disturbed ground becomes easier to clear. Carbon stored in vegetation and peat can move into the atmosphere. A collection of local decisions can therefore become a regional transformation, especially when separate projects open the same interior to roads, workers, vehicles, markets, and new forms of settlement. What appears scattered on a map can become connected on the ground, with each opening making the next one easier. That is why the present threat has a character unlike the catastrophes recorded in the Congo's geological past. The forest is being evaluated while it is still alive. Its timber, minerals, oil, land, and wildlife can be assigned prices before the ecological consequences are fully understood. The system facing those calculations has no institution of its own to negotiate the terms. An okapi cannot contest a concession boundary. A gorilla cannot submit an objection. Peat cannot speak for the carbon accumulated through thousands of years of waterlogged growth. The forest itself has no mechanism for telling a distant decision maker that a particular clearing belongs to a relationship older than any market. For roughly 1.6 million years, the Congo adapted to forces that simply happened. Now it faces a force that can look directly at the forest, measure its contents, estimate their value, and decide whether removal is worthwhile. That is the difference between surviving change and surviving desire. There is a particular weight in realizing that the Congo's future is no longer being decided by the forces that shaped its past. Geology will continue its patient work. Rain will continue to fall, and rivers will continue to move through the basin. Evolution will continue as it always has. Yet, the continued existence of this forest now depends, in part, on decisions made by people who may never have entered it. Those decisions take place far from the roots, wetlands, and animal paths they can alter. They appear in legislative chambers, corporate boardrooms, investment meetings, and development bank offices. A signature can authorize a road, a concession can redraw a boundary, a financing agreement can determine whether machinery reaches a remote section of forest. The physical distance between the decision and the forest can be enormous, while the connection between them is immediate. The Congo survived roughly 1.6 million years without a preservation policy. Its persistence came through the ordinary conditions of a changing planet. There was no institution protecting it from drought, cooling, volcanic disturbance, or shifting seas. The forest endured where its ecological relationships remained viable and changed where they could no longer remain so. The new condition is different because human intention has become part of the system. What makes the moment stranger still is how incomplete our knowledge remains. The Great Peatlands were identified in 2017, after generations of local communities had known of their existence. The Lesula was formally recognized by science in 2007. The first atmospheric measurements in the region arrived in 2020. Each discovery opened another small window onto a system far larger than the portion we have studied. That means the decision is being made while the inventory is still unfinished. We are assigning value to forests whose species have not all been documented. We are altering landscapes whose ecological relationships have not all been traced. We are changing conditions above peat that contains carbon accumulated through thousands of years. We are making choices about lineages whose full histories may never be reconstructed if they disappear before they are studied. The contradiction reaches deeper than the numbers. A forest that helps regulate rainfall, stores carbon, sustains rivers, and shelters organisms found nowhere else is being treated through separate decisions about timber, minerals, fuel, land, and infrastructure. Each decision can look narrow when viewed alone. Together, they determine whether the living system remains connected enough to continue functioning as the forest it has been. The evidence of change is already present. Deforestation records show losses occurring now. Oil and gas blocks have been offered for development. Roads built for extraction can create access that persists long after the original project has passed. None of these are distant possibilities waiting for a future generation to interpret. They belong to the present tense. For most of the Congo's existence, its future was something the planet determined through climate, geology, water, and life. Today, another force has entered that process. Human beings can understand what is at stake, measure what is changing, and still decide what happens next. The forest has reached a point in its history where knowledge carries responsibility, because knowing what stands before us means that whatever follows will also bear the imprint of choice. Every living thing in the Congo carries information that reaches farther back than any human record. A leaf, a call, a footprint, a nesting habit, each belongs to a biological history assembled through climates, migrations, extinctions, and recoveries that unfolded long before our species appeared. The forest, therefore, holds something more unusual than a collection of wildlife. It holds evidence of what Earth can become when its processes are allowed to continue across immense stretches of time. Some of that history survives in forms so ordinary that it can pass unnoticed, yet every surviving lineage adds another page to the record. The okapi is one such message. Its body preserves features inherited from the giraffe family, offering a glimpse of a lineage shaped before open grasslands became the dominant setting for many of its relatives. The bonobo carries another kind of record. Its existence reflects a branch of great ape evolution that developed its own social patterns during the Pleistocene, when repeated environmental changes were reshaping Central Africa. These animals do not explain their histories. Their bodies and behaviors are the evidence. The peatlands speak through matter, accumulated year after year. Plant remains settled into waterlogged ground where decomposition was slowed, allowing layers of organic material to persist for thousands of years. Around 10,000 years of accumulated carbon remains stored there. That material belongs to a period when human societies were undergoing transformations of their own, yet the forest was already building a record underground. Its preservation gives the present a physical connection to a much older climate story. Even the Congo peafowl carries information from a different Africa, one shaped by geographic conditions that no longer exist in their former arrangement. Its restricted distribution reflects a history written through isolation, habitat continuity, and evolutionary change. The species survives because a particular ecological setting remained connected long enough for its lineage to persist. Its presence is therefore more than evidence of biodiversity. It is evidence that continuity itself can become an evolutionary force, preserving experiments that would otherwise vanish from the living earth. None of these messages were prepared for human discovery. They were not protected as exhibits, labeled for future researchers, or preserved with an audience in mind. They remain because the processes that created them have continued. A living species is therefore different from a fossil in one important way. The record is still active. The organism is still reproducing, adapting, interacting, and altering its surroundings. The message has not become a relic because the world that produced it is still operating. The forest also speaks directly to the present through carbon. The Congo Basin rainforest is estimated to sequester hundreds of millions of metric tons of carbon dioxide each year, with one widely cited estimate placing the net amount at roughly 600 million metric tons annually. That means the forest is participating in the climate system now, drawing carbon dioxide from the atmosphere, while its soils, vegetation, rivers, and wetlands remain connected. This is the strange inheritance held inside the basin. The past is not stored there as something finished. It is alive in bodies, behaviors, soils, trees, and relationships, while those same systems continue influencing the conditions of the present. The Congo has never been waiting for humanity to arrive. It has been carrying its own history forward, one generation at a time, and that history remains legible only while the living world that created it continues to exist. Tonight, the Congo rainforest floor is dark, while above it, the canopy gathers moisture and releases it again as rain. Water moves through leaves, branches, roots, and soil, joining a cycle that has no need for human clocks. In the Ituri, forest elephants follow routes learned through generations. Their paths belong to a landscape where memory can pass from one animal to another without a written mark. High in the trees, a silverback may settle into a sleeping nest as another night passes. The tree itself may have stood through seasons beyond any human recollection. Around it, the forest continues its own exchange of pollen, seeds, insects, fungi, roots, and fruit. Nothing announces the age of these processes. They continue through repetition, each generation inheriting conditions created by the generations before it. South of the Congo River, bonobo families remain separated by a waterway that has limited movement between populations for roughly 1.5 million years. Their calls carry across the forest as living expressions of a lineage shaped by that long separation. Elsewhere, the okapi moves along paths that may never appear on a map. Its presence belongs to a world where much remains unrecorded even now. Far below the surface, the peat continues to accumulate. At roughly 7 meters, which is about 23 feet, layers of partially decomposed plant material remain protected by waterlogged ground. The process has continued for around 10,000 years, storing carbon that would otherwise return to the atmosphere. For most of human history, this immense store existed without our knowledge. Its scientific recognition came only recently, revealing another function within a forest whose importance reaches far beyond its visible trees. The Congo also remains unusual among the world's great tropical forests because enough of its standing forest survives to maintain a strong net carbon sink. That living capacity connects the ancient landscape to the modern atmosphere. Leaves draw carbon dioxide from the air. Roots move through soil. Wetlands retain water. Rivers carry dissolved material toward distant channels. The forest is part of the present climate system while carrying a history that began long before modern civilization. So the last prehistoric world on Earth is still here. It does not survive as a memory preserved behind glass, or as a fossil waiting for reconstruction. It exists as a place, functioning through countless relationships that remain active from the forest floor to the canopy. Across roughly 500 million acres, life continues in forms shaped by deep time. An elephant walks, an ape builds a nest, a bonobo calls across water, an okapi follows a trail. Peat gathers below the roots. Rain forms above the canopy and returns to the ground. Each action belongs to the same living system, continuing without ceremony. The Congo does not know that people call it the last one. It does not know that satellites watch its canopy or that researchers measure its carbon. It does not need to know. It continues according to its own rhythms, carrying forward lineages, ecosystems, and processes that began before our species had a name. And perhaps that is the clearest fact with which to leave it. The forest is still here. It is still running, still breathing, still making rain, still storing carbon, still carrying the evidence of a world that existed before us. For now, inside our modern world, that older world remains alive,